Good morning, all. I welcome you all for today's webinar on mastering antenna design and placement with CST Studio Suite. As I see, there are a few attendees who are still joining. We'll wait for 2 more minutes and we'll start the webinar. Thank you. Uh, I welcome you all for today's webinar. I'm Sindhu, working as an application engineer at Beacon for electromagnetic products. So today we'll learn how to master with the antenna designs and placement using CST Studio Suite. So today let's look into the following agenda where we will see through introduction to the CST Studio Suite. Then we will see how to choose right antenna, then optimizing the antenna placement, antenna integration into the CAD model, and also the antenna performance, where we will see each by each what it means. So to start with, we have SIMULIA portfolio, which comprises of various modules and tools, which is suitable for designing, whether it could be the schematics or the 3D simulation part. PCB and packages. We have antenna magnets for antenna design, then filter design 3D for filter designs, then CST chip interface for designing the chips, then FEST 3D, and also the Opera for low frequency related application. So to look into the detailed description about what each of the modules in CST comprises of, we can work with static and low frequency applications where we have various types of EM devices, or if we want to see or design a magnet, what is its fields, we can view or calculate the fields and observe the field patterns over here, where we can also do high voltage and heavy current analysis. We can design and analyze the sensors within CST Studio Suite. Then we have microwaves and RF or optical types, where we can analyze various design and analyze antennas, circuit components, radar cross section, then biomedical exposure, SAR, optical applications, and also the periodic structures. Then coming to the EDA or electronics, where we can make use of PCB and packages, where we can import the EDA into the CST interface and perform the analysis like signal integrity, power integrity. Then we can perform SIPI co-simulation, then broadband model extraction, design rule check. All this analysis can be performed. And coming to the EMI EMC part of it, we can do analysis related to radiated emission, conducted emission, then conducted susceptibility, radiated susceptibility, and also with respect to the components as well. Then we have particle dynamics, where we can see the particle behavior of like accelerator components, vacuum electronic device, and space related applications, or the beam optics related analysis can be worked over here. So this is the brief introduction to various modules and tools which is available in CST Studio Suite, comprising of various templates which is already available within the CST Studio Suite, where the designer or the analyst can make use of those templates to design and analyze the various types of electromagnetic devices or components. So now in today's webinar, I'm considering a beam, that is a projector, where we will see how we can fit in the antenna into the BEMI for various applications like for Wi-Fi connectivity or Bluetooth connectivity. So when we talk about any digital things, the main thing we'll look for is the connectivity. So the primary requirement here for BEMI is also the connectivity, where if you can't connect wirelessly with high data rates, it is basically a non-functional device. So the questions which come to our mind when we are designing any electronic devices with any wireless communication is, can be connected wirelessly to any network or stream data from the web. So all other thing which also comes is can be connected via the Wi-Fi or Bluetooth to the devices such as laptops or tablets. So here we will see our platform basically today is to discuss on two questions. That is, how can antenna design keep up during a dynamic product design cycle with changing constraints which is caused by various inputs from other design teams, and also how can we ensure that we are ready for future communication standards by exploring new concept antenna designs earlier. So we'll see step by step how this is possible, how what are all the steps involved in finalizing the design with antenna installed into the beam. So to start with, initially we will look for the CAD models from the mechanical team and choose the potential positions to place the antennas. Then as once we design the positions to place the antenna, we have to look for the suitable antenna with good performance, and after placing it we have to see build the assembly, install it into the assembly and evaluate the individual performance, and also the installed performance of antenna, and look for the total scan pattern or the directivity of it or the far field related results, and see if it is able to perform well. And then if it fails to, then we have to find the complementary combinations which is best suitable to provide the better performance and evolve to the market. And then if we have any small changes, like what is the purpose of a small selection with respect to the practical solutions, same, the cycle repeats. First, we will choose the antenna, place it, see its performance. If we have to make any necessary changes, we can get back to the antenna magus and do it. So I've been telling about antenna magus. So I'll just give you a glimpse about, or just say what antenna magus is. So Antenna Magus is a software tool for acceleration of antenna design and the modeling process, where it has a huge antenna library of around 350 antennas, where we can make use of those antennas as a reference design and make necessary design modifications to get the respective radiation pattern or the coverage coefficient of it. So here, this is the BME model, where it has various speakers, batteries, it has frames involved, and the projector unit, electronics. So all these are available with the total height mentioned. So the first question what antenna analyst or designer would look for is which are the locations which are suitable for us to place the antennas. So here we have various variants like frame designs. Usually when we are designing any new component or a device, we will come up with various variants. So we will have to know like which of the variant is suitable. So it's just not one team is going to decide how exactly the device is gonna look. So it involves various designers, whether it could be the CAD designers or the mechanical simulation people, the structural people, or the electronic design team or antenna designers. All of them have to come up with one single device which is suitable for all of their results to be put in. So even here, we will have to look for which are the spaces which is left for the antenna designers by discussing with different teams. So here we can see green regions are the places where the antenna designers can make use to place the antennas within the gaps in the frame. So once we come up with the positions or the gaps where we can fit in the antennas, the next thing is to choose the antenna. So when we have to choose the antenna, there are two ways. One is the designer will think to ease the process or to complete the design cycle at a faster rate. We will look whether we can purchase it by going to some shop where we get the off-shelf antennas, or do I have to custom the design? So for each of the cases, there are pros and cons. When it comes to off-the-shelf antenna, we can go purchase the antenna which is suitable for, let's say I need antenna of certain volume which will fit into the design. So I look for that. When I look for such antennas, the performance might vary. Like it might not be suitable for the application what I'm looking for, or the results what I will be looking for. So at that cases, again, we'll have to go purchase, for which a lot of time and also money is spent on it. And the other thing is, what if it doesn't work? Can I simulate, or what I have to do? That is the next question when it comes to off-shelf selection. Whereas custom design is better because we will know initially with the help of antenna maggots, we can come up with few of the designs which is suitable for placing the antenna in the respective position for the given gap, and we can redesign it or retune it to get the performance what is required. So rather than spending on off-the-shelf antenna, we can custom design with the necessary libraries which is available within antenna maggots. And after thinking about it, the next question comes is what are the types of antenna we are looking for? What is the frequency of which we are going to match and show the performance of the antenna? So here for this BME, we will be looking for LAN 2.4 and the Bluetooth connectivity. So here in antenna maggots, we have various templates or the specification chooser with respect to various industries like aeronautical or ISM, then for the public broadcast, radar band, smart devices, and if we want to choose with respect to the custom specifications, we can do that as well. Since we are looking for a smart devices and mobile communication types, we can choose that particular template as highlighted over here. And then within that, we have various applications, that is, whether it is for cellular bands or GPS or UNII, and then LAN, WiMAX, then personal area network. So these are various other sectors which comes within the smart devices. So here, since we are looking for LAN, we can choose that. And the next thing is we have to look for the specific name and the frequency at which it is operated, and we have to understand about the detailed specification of those type of components. So once we choose it, here within antenna maggots, we get to see there is a keyword list where we can filter it out by selecting the type. So here I'm looking for a compact type, integrated antennas, and a bland type model, where it will show that or it will filter out all the antennas within the antenna maggots which is suitable with respect to the keywords what is being selected here. So we can see around 33 templates of antennas are available here. And by just looking at the design and the name, we will not know what are its details. So, and also the other constraint is the antenna has to fit in that particular gap. So here we can define the volume of the antenna which we are looking for, where here you can see omnidirectional antenna is chosen and the frequency values are set, and we can provide the group properties with respect to volume. What is the total volume of the antenna you're looking for? So once you filter it out, now from 33, it is showing 22 templates where it matches almost the specifications what we are looking for. And then here, if we have to look in detail or the quick summary of what that particular antenna is, like what is the quantity, like what is the polarization, radiation pattern, what is the gain, performance bandwidth, complexity, impedance. So all this quick summary will be provided once we hover the mouse onto that respective antenna, where we can go through all those details and choose them. So let's say I'm hovering over the other antenna, that is substrate mounted normal mode helix type of antenna, where we can see the polarization type, then the radiation pattern, the gain value, and the performance bandwidth, which is like here this antenna will have all the dimensions placed, and it will be designed as per the standard, and we will be seeing the results like the radiation pattern, far field, all the details will be captured here. So once you choose it, like basically when we are working with any type of design, initially we will not come up with one particular antenna and say that we are going to run the analysis for this and install it in the assembly. We will have to compare the antennas where we might have antennas similar to each of its performance with certain difference, and also here if you see we have something called collection, where based on the filters we had around 22 types of antenna, out of which 10 such antennas which we are interested or which is similar to my requirement, I can collect it and then I can perform the analysis over here. That is the comparative study. And then I can also cross check with the sizing. So since my volume was 10 into 10 into 10, so here I'll just check whether the size is proper for me to fit into the spaces within the beanie. So here, since we have chosen around 10 antennas, we have to just cross-check whether the size requirement is met by each of the antenna. So here, if we see towards the left side, we can actually fit this antenna into the designated space, whereas the other one, which is towards the right side, that is wire monopole with ASA for WLAN antenna. It is circular in shape, but meeting the requirement what is being fed, that is the volume is matching here. But we cannot fit this into the frame, which where we have certain space around volume of 10 into 10 into 10. So this, though the performance is good, we cannot use this type of antenna into the beam. So we can neglect this particular antenna and go ahead with the one which is suitable for its position. So next is, once we check the size, that is similarly here there is one antenna which is similar to off-the-shelf antenna, where we can reduce the size by reducing the relative permittivity within the antenna maggots. And here, based on the requirement, we can modify the design and also match with respect to the frequency what we are looking for. That is, the reflection coefficient has to match with the one what we are looking for to place within the beaming model. So even the modification is can be easily done within antenna maggots. So now, out of 10, the 6 antennas which is most appropriate for my designing is now available. Now I have to come up with one single design rather than placing all of the 6, or I can come up with a maximum 2 of it, which is good at its performance and suitable to be fit into that particular gap within the beam. So for that, the next step, how do I rule out, is I can form the compare tool, where I can compare the results, where I can cross check what is the bandwidth percentage of this, and I can just come up with 1 or 2 antennas which is most appropriate to provide the good performance. So here, if I look at the WLAN antenna with 2.4, here the second one provides better bandwidth of around 16.59%. So I can choose them. Also, towards the right side, you can see it provides the reflection coefficient plot and also far field versus angle when we are comparing various antennas together to see which provides me the better bandwidth, or whatever the requirement which I'm looking for, if it is meeting my requirement or not, can be compared here within antenna maggots. So once that's selected, next thing is, so now I have come up with one single antenna which is meeting the requirement what I had listed initially. So now after the antenna is being modeled, the next thing is to import it into the assembly. So how can I import it is with the help of anchor points, where we can define it as a connection points towards the entry of the antenna and place it or snap it onto the frame where we want to position or locate the antennas within the beanie. So here you can see with the help of anchor ports and anchor edge, we can snap it and position it to the location where we have designated the place within the beanie. So after that, the next thing is to, like once the anchor points is set, the next thing is to provide the local meshing. So we know with respect to the electromagnetic simulation, which are the positions where we need to finer the mesh or where the meshing details is much necessary. Rather than providing the finer mesh throughout the entire assembly, we can provide it to the locations where we know that there could be electromagnetic requirements for us to fine tune the mesh to get the results accurately. So even here, we can see through the ports, like near to the ports or near to the antenna, we can have the finer mesh. Whereas towards the other sides where there are a few of the components like speaker or battery, we can provide normal meshing than a finer mesh. So here you can see this is how we can mesh. So here you see there is an antenna which is positioned. So we have finer mesh throughout where the antennas are being positioned. And here within CST Studio Suite time domain solver, we are making use of PBA meshing, which will help us to, so here you can see if there are any complex structures, it will help us to provide a better meshing. That is, PBA deals with very complex CAD, and also if we are doing any local meshing, like with respect to the antenna feed points or any kind of antenna details, we can provide the finer meshing and get the analysis done by minimizing the number of mesh cells, so that the time taken to run the analysis will also improve. So now, after like here, two things come up. So initially, we would have run the analysis for individual antenna. So next, once it is installed into the assembly, we have to check whether the antenna performance is the same. So here, if we see design for free space, that is without antenna being positioned within the assembly, what was its performance? So here you can see around 2.4 gigahertz is the performance. And then once it is placed into the beamy, so here you can see within the beamy on top, there is the antenna which is placed. So once it is placed, the performance is degrading. It is almost 2.55 gigahertz. So this is one of the challenge what any antenna designer would come up with, where individually they would have struggled a lot to come up with one antenna design. Then when it is placed into the assembly, the performance degrades or deteriorates. So again, they'll have to redo or recheck. So when we are making use of off-the-shelf antenna, so this is one challenge which will come up. So initially they would have bought the antenna which is specifically designed for certain frequency, but later on, once it is positioned into the assembly, it deteriorates. So it is of no use next time. So customization here comes well fit in for this kind of applications where you are dealing with a completely new product design. So now, since it is deteriorating, the next challenge for us is to get it back or retune it to the frequency what we are looking for. So initially, the design in Beanie, with the help of antenna maggers, we tried modifying the antenna with a shift of 200 megahertz, where we can see the performance is still low. So you can see it is below 2.4. And then we made a phase shift. We made a shift of 120 megahertz. So now it's almost matching with the one when it was individually performing around 2.42 or something. It is matching. So we can make use of antenna maggers to retune the same design and get back to its specification, providing the better performance. So now we can look through the electric fields. So we have just designed the antenna. So now as we will try to place it at two different positions and see what is the electric field. So here we have antenna 1, which is placed towards the left upper corner. And on the other side, we have the electric field of the antenna, which is placed towards the right side of it. And also we can view the gains of the antenna. So here the antenna will radiate usually in this gain pattern. We can see the 3D view to check whether there is any better coverage, or like if we can improve the coverage of it. So here we can see there is a clear holes in the coverage, and also we can also calculate the total radiation efficiency of both the antennas. So if you see here, antenna 1 total radiation efficiency is around 85.6, whereas the antenna 2 is providing a total radiation efficiency of 90.5. So there is a scope of improvement over here. We will see through how we can improvise in for this lab. So here we also can cross-check, like instead of running the total scan pattern for both of it, we can individually activate the antenna, like each of them, and then record what is the maximum gain with respect to the frequency and the theta value, how it is going to change the total scan pattern. So basically here we will get to know what is the coverage efficiency. So basically coverage efficiency is nothing but the coverage solid angle, that is theta with respect to the maximum solid angle, pi, where we can see we can measure it, we will be measuring at 0 dB, 2 dB and minus 3 dB. Basically, why we are measuring at this is if we are getting 100% coverage at 0 dB, then we can say that our antenna combination is better than an isotropic radiator. Whereas if 2 dB is around 100%, then it is we can say its performance is better than dipole's peak gain. So we have to see such that the coverage efficiency is much better, so that the connectivity with respect to other devices like laptop or other electronic devices, it's much better, or the tablet is much better. So now, since we saw that there was a scope of improvement for better coverage, we will now look through the placement strategy. So here we have what we are doing initially is we are trying to place two identical antennas within the beaming to see how well the total scan pattern or the radiation pattern we can get to. So here if we see initially when both of them were placed in the top front, various types of total scan pattern we can observe by positioning at different positions. As you can see, there are 4 different types of antenna placement positions here for which we can see the total scan patterns. And then once the position is changed, we can see there is a difference in total scan pattern. And after running these total scan patterns, we can make use of the comparison to see which is the best design when we are trying to place it by positioning at different locations. So MIMO characteristics here shows not much difference in diversity gain, where all are better than 9.82 decibels, or envelope correlation coefficient here are all below 0.38%. So if we look at the coverage efficiency here, we see through there is a big difference between the best case and worst case, which is around, it is greater than 2. Around, if we see here, the 8th one, here we say that it is worst case, whereas the 6th one, which is the antenna on the right inner and left outer, which has got around 55.9%. So if we compare 6 and 8 results, it is around 25% difference. Also, we can see the graph over here with respect to minus 3 dB, 0 dB and 2 dB measurements. We can get to see what is the best and worst case performance. So by doing this total scan pattern comparison, we can come up with the better results, or we can say that which position of antennas provides the better coverage efficiency. And then let's say if there was some problem with the frame, and if I have to make necessary changes with respect to the placement. So here initially we placed similar type of antenna at different positions, and we checked what is the total scan pattern and which provided the better coverage efficiency. Now we will look through 2 different complementary antennas which is positioned at different gaps. As you can see towards the right top, we have spaces which is marked in green where we can position the antennas and check. So here initially, since we have around 6 to 7 types of antenna which are different, which are intended to work for the respective frequency what we were looking for, we will try to place it at position 1, that is right next to the speaker, left side of the speaker. So here we can visualize the total scan pattern, and then with respect to the position 2, we can get to see all the scan patterns of 7 different antennas. And then when both the antennas are positioned at A and B, how well the scan pattern can be seen, can also be visualized. So here if we see initially at position 3, A does not fit into the size. I mean the respective antenna which is selected here is not fitting into the gap. So there could be such challenges where we can ignore such types of antenna and choose which is fitting into the space and also providing a better total scan or the coverage efficiency can be selected here. So now, with respect to the different antenna combinations here, we can see which type of antenna provides a better coverage area. So if we see if the antenna is positioned towards the right side of the, next to the right side of the speaker, and there is one more antenna which is positioned at the bottom of it. So based on the total scan pattern, these two were the antennas which were selected, and we can see which provides the good coverage areas. And here, if we see, there is a very poor coverage area, which provides the scope for improvement. So we can see that at 0 dB, the total coverage efficiency upon choosing various types of antenna with various antenna placement positions, we got the coverage efficiency to be 85.3, which is appropriate. So now, let's say I have come up with one particular antenna with certain antenna placement location freeze. I will send this design to the CAD team again to continue with their process again. By then, maybe with other teams, they would have interacted and there could be few more components added, or there could be a change in the battery size, or they will come up with certain variants again. So at that cases, we will have to rethink and retune or redesign the antennas. So even here, let's say with the small battery variant, if our design team come up with a new frame, we will have to do several other space check and replace the antenna or redesign the antenna, which is best suited or best fits into the position which is allocated. So here are two cases where from the previous to the current design, initially there were few spaces above the batteries where we could position the antennas, but now when the battery size is large, there is one more variant which is added. Even for this, if we have to design the antenna design, we can make use of antenna magus, which is much faster since we have the set of antenna libraries which is available, so that we need not start from the scratch. That is, we need not go through that certain reference paper, or we need not go to any customer or the shop to get the data sheet of certain type of antenna which suits the requirement for my design. I can make use of antenna magus. In short time, I can choose the type of antenna which is suitable with respect to the filters, what is available within that, and I can start placing the antenna and check its performance rather than looking for which type of antenna will best suit for my design. That is one of the added advantage of making use of antenna magus in CST to perform this type of analysis. So here, as I said, initially we had a total volume of 10 cross 10 cross 10 mm. Whereas now, based on the change in design, now we are looking for 2.45 gigahertz operation with 20 cross 12 cross 12 mm volume. So based on this volume, antenna magus will help us to filter out the suitable type of antenna which fits that volume. So here I have around 11 types of antenna which meets the requirement. And then I can test it in all 4 locations where the places have been allocated for antenna designers to position their antenna. So here we can see 4 different types of antennas with the same variant can be positioned, and we can perform the analysis. So here we see that these two are the antennas which is best suiting the requirement and also fits well. So when we take that, we can proceed with the total scan pattern or check what is the coverage efficiency. That is, antenna 2 and antenna 5 are considered here, which is placed on right center and right top of it. So we can observe the scan pattern over here, and we can see that it provides a better coverage efficiency of around 98.3 over here. And with respect to the 0 dB, it is around 61.9%. With 2 dB, it is around 58.7%. So then if in case if we want to confirm with new design combination, let's say previously we worked with small batteries where we had a lot of spaces to position the antenna. Now with the new variant, when the battery was large, we had different spaces for us to fit the antenna. So if we compare from the previous design with change in slots or positions, if we compare both the results, we can see here towards the left side, we can see the S parameter plot, and that is S11 and S22 parameters for both large battery variant and small battery variant. Like we can see what is the frequency it is working with, and also the dB. Then with respect to the total scan pattern, we can see observe the coefficient, coverage efficiency. So with respect to the large battery variant, we have around 81.9%, and comparing it with the other one, that is the small battery variant, we have around 69%. So here the other, so once we do this comparison study, we will come to the conclusion that about how well the antennas are placed and what is the best coverage efficiency we can come up with. So similarly, every time when we are designing or analyzing the antenna for various types of applications, we can make use of these steps. So it is better to design the custom antennas. Also, here, since we have the set of libraries, designers might not struggle or they don't find it difficult to make use of such antennas. So the antenna magus is a very good tool which helps me to choose the design, then customize them, see what is the S parameter plots, or what is the far field details or the directivity details of each of the antenna, providing a brief summary over various types of antenna within the library, and filter it out based on my requirement and choose them. So another added advantage is if you want to further customize the antenna from the antenna magus, you can export the antenna designs from antenna magus, get it into the CST Studio Suite, and you can customize the design and then assemble it within the assembly and do various types of analysis, which is easier, where you need not make use of any file conversions, is not necessary, where you might lose data with respect to the port definition, or material details will not miss, since there is a direct export to CST Studio Suite of all these antennas. So then after performing the analysis, when the design best suits, we can send it back to the team saying that the antenna placement and antenna design is meeting the requirement, and it is good to go with the next set of processes. So once after doing the antenna design and sharing, just not with the frame or with the different types of antennas, there could be changes. There can be changes due to various electronic designs. Let's say if I have PCBs or any electronic devices within that particular device, sometimes the pattern might also change due to various other electromagnetic factors which is coming in contact with it, right? So we will also have to take into account those details. Then there can be certain other issues with respect to the power, or with respect to the cabling, where there can be EMI/EMC issues which can change or alter the performance of antennas. Then we can also have, let's say, the projector unit here. So if there is any changes in the projector unit design, if they are going to modify the design, then there can be chances of changing the space constraint, where we will have to look for smaller or compact antenna designs. So these are some of the other challenges the antenna designers might come up with. So we have to look into all these constraints. So let's say if in case if I have to avoid all of this and come up with final product, we can make use of CST to see what are the issues or challenges which will come up with all these types. Since we have PCB and packages, we can perform the analysis for electronic designs. Like if I have to check the signal integrity, power integrity issues, or the design rule check issues, then coming to the power or the cabling issues, we can see what is the crosstalk, or we can see what is the EMI/MC issues, if there is any radiated emission, conductor emission, or susceptibility, which I'll have to look into account. I can perform the analysis by turning on various types of antennas and see if that is going to affect. So the whole package is available within CST Studio Suite with various types of applications where we can run the analysis and come up with a better antenna performance or better data rates with respect to the PCB, or come up with minimal crosstalk where the data will not be of any loss, or we can check the complete performance of the various electronic and mechanical aspects taking into account, and come up as a new product over here. So this is what I had for today. I think it was a interesting session where it helps the antenna designers to understand like what are the methods which we can follow to ease the process by considering just not antennas with various other constraints within the devices, how we can come up with the best antenna design, providing better coverage without any affect or harm with other electronic components over here. So if you have any questions, you can post them in the question or chat window over there. I'll be happy to help you. To answer the question which is asked by Mr. Siddesh Chavan, so you have asked how many antennas are there for near field applications. So we have around 350 plus various antenna designs which is available within the antenna makers, and we keep adding some of the antennas with the service pack. So here to answer your questions, we have around hundreds of near field related application antennas, so you can make use of it. Where it's asked that how to ensure that we cover all possible positions for best placements. So basically here, as I said, once we are designing a new product, so basically it will have various other components as well. Initially, we will have to look for which are the spaces which is left for antenna designers to come up with a good antenna design for better coverage. So basically, based on your internal teams, you can discuss and look for which are the positions. So based on that, you can try various permutations and combinations by positioning similar type of antenna, or if as per your design requirements, if you have to place two different types of antennas which is operating at different frequencies, you can just initially place at the required position and just cross check with the better coverage. You'll get to see what is the coverage efficiency. Based on that, you can decide which is the best suitable position. Okay, there's another question by Purna. So it's asked that like what if the gain need to be increased and they may not fit in the provided space given by the CAD designer. So that's what here, if you've seen throughout the webinar, there was one slide where I knew that I had a total volume of a certain range. So based on that, you saw how we retuned by making a shift of frequency that is from 200 megahertz. We changed it to 120 megahertz by just retuning it. So basically, a similar way we can retune the performance of it and get back with the respective gain. So there's one more question by Mr. Danaji. How many antennas are available for automotive applications? So even there are lot of antennas with respect to automotive application as well. So we have various templates under which there are multiple hundreds of antennas suitable for that. You can make use of them. So for a couple of more minutes, I'll just wait to see if there are any further questions. If not, we will be closing the session in next 2 minutes. Please post your questions if you have anything, or you can get back to us. Here, I have put on the email ID where you can post your questions, or if you are interested to see the detailed demonstration on antenna design and analysis, you can just request us by letting us know the date and schedule so that we can come up to your premises and give you the detailed demonstration on all this. Okay, thank you all for attending this webinar on mastering antenna design and placement using CST Studio Suite. And as I said, if you have any further questions, or if you are interested to have a detailed demonstration on CST Studio Suite or antenna related applications, you can please revert us back to any of these email IDs. Thank you. Have a great day.